All right, so I think we are now live. So hello everybody, welcome back to yet another edition of Quarantine Thermo. Thanks for joining us again. So today I'm very pleased to introduce Dr. Raam Uzdin of the Hebrew University of Jerusalem, who is of course well known to many of you or most of you, I imagine. So Raam um, is an expert quantum thermodynamicist. He's made very important contributions to kind of, let's say, more concrete implementations of quantum thermal machines, but also the more kind of fundamental abstract side of quantum thermo. And it seems like his talk today is going to kind of combine a little bit both of these themes. So I'm very excited to hear what he's going to tell us about. So before I hand over to Raam, I'll just sort of reiterate the usual thing that I do, which is just about the format. So basically, Raam's going to, as usual, speak uninterrupted for as long as he wants, and then we'll have questions and answers at the end. So if you have any questions during the talk or at the end, please just write them in the YouTube chat window and make sure that it's clear what your name is so I know who's asking. So yeah, without further ado, I'll hand over to you, Raam, and I'll remove my video and you can take it away.
Great. Hi, everybody, and thank you, Mark, for the kind introduction, and also to you and John for organizing this. I join all the other speakers that think that this is actually brilliant, and I think just in this specific talk, you'll see several references to talk recently given in this format, and I think it's a clear indication for the interaction it creates. So, thank you for this. The topic is periodicity inequalities, which is slightly different from what we usually explore in thermodynamics, which is the countings of heat, energy, and entropy. And I hope you'll find it interesting. Right, so if we think about the needs of the new world, new experimental world, and in particular the quantum world, so we see that there are several differences from what we had so far. In particular, setups like ion traps or cold atoms in optical lattices or superconducting circuits, they require huge resources to control these elements and to keep them isolated and to cool them. And even calibration itself is a resource that is very important. And this raises the question if efficiency and COP for refrigerator and even energy itself, if it's still relevant, because these machines may do a task which is not even energetic. Okay, it can do some computation or something else. And along these lines, I would say that it's hard to answer what is the right figure of merit because there's no clear leading application that can guide the theory. And here I refer to the interesting suggestion by Geraldine Hack and her collaborators about machines that create entanglement. But still, we are missing something like the historic steam engine that gave a clear direction to the development of the theory. So in our view, what we currently have is these noisy intermediate scale quantum computers and simulators. So we see them, at least in my group, we see them as today's steam engines. And here again, I refer to Michele's talk, who talked about his experience with a D-Wave machine. And this reminds me of this scene from the Hitchhiker Guide to the Galaxy, where they build this computer that computes the meaning of life for 7.5 million years. And in the end, it says, yes, I thought it over quite thoroughly, it's 42. So of course, the first question is, what does it mean 42? But the second question, which is not often discussed, is how do we know that this answer is actually true or reliable? Of course, we can do it again. It will take quite a lot of time, but it's quite problematic how to verify a result that we cannot actually compute. So how to cross-reference it and have confidence in the machine that we built. So this verification is one of the challenges associated with these machines. And if you read the quantum supremacy paper, you'll see that this is actually an issue there. So one of the way to approach this is to use thermodynamics, because it's not sensitive for the complexity of the evolution. However, there are quite a bit of issues, but just to name two. One is that thermal states in isolated microscopic setups like these optical lattices are somewhat artificial, and often they have to be created from a vacuum state or from the ground state. And this is quite costly. For example, in the experiments that we do on the IBM computer, if we have n qubits, we need 2 to the power of n circuits just to create the thermal ensemble. So, and this is, most of the experiments just goes to create this initial condition. Pure states are very natural and easy to use. Unfortunately, in thermodynamics, they lead to trivial predictions. And this is associated with this ultra-cold catastrophe that Andre was talking about in his talk. And also in this paper, we offer another solution to this problem. But this can be remedied or averted when one of the object is very cold. But if the whole setup is in the ground state, then I'm not aware of a way to adapt thermodynamics to cope with this scenario. So usually the prediction is just that the population of the ground state will increase in time, okay, and that's or remain the same, which is makes it completely useless. So let me start by stating something obvious, because this is actually what we're going to change from the regular paradigm. So usually in thermodynamics, and it doesn't matter if it's the Clausius-Lindblad inequality, resource theory, thermodynamic uncertainty relations, or more generally fluctuation theorems, there are 2 time points: initial and final. And the initial state is usually a special state where, let's say, that the elements may be uncorrelated typically. And in general, there's a certain notion of temperature related to this initial state. And that's what makes thermodynamics in some sense. The final point can be chosen at will. There's actually no limitation. However, once you fix it, there's no information on what's going on in the middle. Alternatively, if information about the expectation value in the middle is provided, there's no way to exploit it and use it in order to get better prediction on the final point. And again, I mentioned that presently in thermodynamics, it doesn't work well with pure states. So these are the two things we're going to play with and change a bit.
Raam, can I just check? You're still showing your first slide of the talk. You haven't? Have you been
No,
moving?
no. I changed them. Wow.
Okay. I'm sorry. So then this hasn't worked. So can you try just maybe exiting share screen and doing it again? Sorry about this. So
yeah. Okay. Well, I think I'll have to stop and share again.
yeah. Sorry, that's my bad. We should have double checked this at the beginning.
Okay.
Okay. So now we can see this slide.
Can you keep moving?
Yeah. No, at the moment it's just still fixed on one thing. It's not changing.
I'm pressing resume share, but nothing.
No, I can see your screen, but I just can't see you flicking through the slides. You see.
And I do.
Okay.
Again, I'm doing
So
sharing.
Sorry, this is not a problem that I anticipated. I kind of thought if you're
Yeah.
sharing. So
I can try and close Zoom
yeah, so
altogether,
maybe we
or
just try and very quickly restart this, I guess.
okay.
So sorry about this, everyone. Let's just try and restart the call, and then we'll be back with you very very shortly.
Okay, let's do that.
Okay, let's just try that again. Yeah.
All right, can you hear
Hi,
me?
I can hear you. Yeah.
Okay, let's try screen sharing. Can you see it
Okay.
moving?
Um,
It's not moving?
no, it's not moving. But what we can then do is maybe instead of, so I would exit full screen because you're in full screen right now, right?
Yeah.
I mean, exit full screen. I would say let's just go through the slides this way. Sorry about this, but unfortunately, I think this is an
Okay.
issue with Zoom or something to do. I mean, this is very strange, but I don't know why this is happening. Maybe it's something to do with you having multiple screens open. Um, but in any
Mm,
case, we can see your
there
slides
is,
from your.
maybe. I don't know. Well, I mean, it's the usual Mac stuff, so.
Yeah, I
Um,
mean, I've never had this problem before. But unfortunately, these things seem to be highly non-deterministic. So, in any case, this works fine. I mean, we can see your slides fine like this.
yeah,
Although,
but I have a lot of things that, well, not complicated animations, but
do you have multiple
okay.
screens open, Ram? Because if so, maybe you should just get reduce everything to
Okay,
one screen.
wait. So there's another.
Sorry, by the screens, I mean multiple displays. I mean, if you have multiple display monitors active.
No multiple displays. Um, let's just give it one more try. Share.
Again, I apologize to everyone for this, the usual thing. Some kind of. So now I can see your mouse moving. Yeah, there we go. All right, perfect, perfect,
Okay,
perfect. Okay,
okay.
this is good. We don't have video for you, but you can restore that if you want. Um,
There we are.
Perfect. Okay. All right. Thanks. Sorry about that, everyone. So we're back in business. So please go ahead, Ram.
Great. Okay, so here now you can see what I was talking about. And this is the illustration for this 2-point feature of standard thermodynamic theories. And okay, this is the point that we stopped. And our approach is based on the principle of global passivity. And I'm not going to introduce passivity in the usual way. I'll just state what global passivity is. I think it's shorter. But of course, it's intimately related to the standard passivity. And it states the following. If you take the initial density matrix of your whole setup, okay, when I say setup, it includes all the environments in the system, and the setup evolves unitarily because it includes all the elements that interact with each other. Then it's possible to take this state, this density matrix, and turn it into observable by taking some monotonically increasing function of it. So this is an object that you create with the minus sign, and then it's guaranteed that this expectation value will grow in time, not necessarily monotonically, for this you need Markovianity or weak coupling, but it will grow with respect to the initial value. So just to be clear, the operator, which represents the observable, doesn't change in time. So if we calculate this at the final time, the expectation value reads like this. Okay, so this is fixed in time. What changes is the density matrix, and it evolves unitarily. In fact, it can be also bilinearity. It can also be a mixture of unitaries. So now we immediately get families of inequalities, and let's look at a specific one. If our initial state is a collection of thermal environments, for example, like in an absorption refrigerator, and we make the specific choice for F, we get the following family of inequalities, where alpha can be any real parameter. So each value of alpha corresponds to different member in the family. In particular, if we take alpha equal 1, we get this simplified form of the second law without the entropy of the system. And this is exactly what we've seen in Michele's talk. So the question is, what new information these strange-looking inequalities contain? So we made this experiment that provided, I think, a very clear demonstration that they provide something that the second law cannot. And the idea was to detect that our system is actually open by making a measurement only on the system. So we had 4 qubits. One of them constitute the environment, the thermal environment that we can either couple or not to the system. And we had 2 hot qubits and 1 cold qubits. And the goal is to measure only this visible part of the system and see if the environment is connected or not. And of course, if it's disconnected, the evolution will be unitary and all the inequalities should hold. But if we'll see that one of them is violated, it means that the evolution is not unitary, and therefore we have a heat leak. So here you can see this inequalities that I showed you earlier. And if the change is positive, it means that we don't have a detection. If the change is negative, it means that we have a detection. Here, just as a reassurance test, we disconnected the environment, and you see that indeed, we don't have negative values. Black is experimental data. This was done on the IBM computer with the uncertainty. And the dashed red is theory. Now, when we connect the environment, we see that if we look at alpha equal 1, that represents the second law, then we cannot detect it because it's positive. It means that there's no anomalous flow from cold to hot. Despite that, if we look on higher order moments, there is something that goes on that is being affected by this heat leak. And we see this by the fact that beyond a certain value of alpha, we get negative values. And it seems close to 0, but actually it's way beyond the 3 sigma uncertainty. So it's a clear-cut detection. And this indicates that they contain more information than just the second law, and that they can be useful. But this experiment is just a proof of principle. It doesn't intend to be too practical. Looking on many heat leak scenarios, both experimentally and theoretically, we gather some conclusions. So first, the fact that we have to use thermostat is what prevents us from doing experiments currently on IBM with more than 5 qubits, because we need to run so many circuits that we cannot do it in sequentially in one time because of limitation, IBM limitations. So we are limited to 5 qubits. And again, it's because it's not a hardware problem. It's just because we need to run many circuits to create the thermal ensemble. It often involves these cumbersome observables, like as you've seen earlier, some powers of beta h, but this power can even be fractional. It doesn't have to be an integer, and it can also be negative. So they don't have a clear physical meaning, well, at least to the best of our knowledge, but we still see that they have operational meaning for heat leak detection. Another thing that we observed using a different framework that we're developing that is called passivity deformation, we saw that there's actually a critical temperature for the environment, that if the environment is hotter than this temperature, it's impossible to detect the heat leak using just observables. And I'm not including all sorts of information quantities, relative entropy, and so on. I'm talking just about observables. So this is impossible to do. The limit where the temperature goes to infinity is it makes a lot of sense, because then interacting with something at infinite temperature, it's a unital maps, and it's we understand why we cannot detect it, because it's like a mixture of unitaries. So the limit is very clear, but here we see that also for a finite temperature, we cannot detect it. And this answers a fundamental question that we asked ourselves. And if you heard any of my previous talks, then this was an open question, whether any heat leak can be detected using these methods, or there's actually a limitation. So there is a limitation. On the other hand, there are some advantages to this method. So it operates as a black box. We don't need to know anything about a circuit. And the observables, even though they are cumbersome and they don't have a clear physical meaning, we can extract them easily from local energy measurements in each shot of the experiment. And in fact, they are not more demanding to calculate than just the average energy. It's the same computational effort. Now I want to switch to talk about these periodicity inequalities, and I want to get there in 3 simple steps. So the first step, or the first observation, is that this global passivity observation that I showed is actually not limited to density matrices that have a unit trace, or to density matrices at all. It's applicable to any object that evolves unitarily. This is the only thing that is needed. And this opens the possibilities to apply to completely different applications. So one I'm going to talk about is this periodically driven system. And the other one is metrology, which is, I mean, I would like to say it's work in progress, but there's not a lot of progress because we are pushing this periodicity stuff, but we do hope to get back to it soon. And I want to make a slight detour and make this connection between metrology and passivity. And again, the fact that it applies not just to density matrices, but also to other objects. So here is a scenario, a typical scenario in metrology. There is a system, and there is a certain parameter that we want to estimate, and this parameter affects the state of the system. And what we want is to couple our system to some particle that we call the dial particle, and this is the part that we actually measure. And from the expectation value of this of this particle, this dial particle, we want to deduce what is the value of lambda. And they start off uncorrelated, of course. So here it is. This would be the expression for the expectation value of the dial observable. And here I wrote the dial observable in the space, in the total space of the setup, not just in the local space of the dial. And this is the final density matrix of the whole setup. Now, if we look on the change in this observable, when we change lambda, so we just take the derivative, and the only part that is affected by the derivative is, of course, the local density matrix of the system, the initial density matrix of the system. And you can see here that it has the structure that we need for passivity. If we want to maximize the change, we will look for something which is, well, not the passive state, but actually the most active state. All we need to do, or all the unitary needs to do, is first to make these two objects commute so that they will be in the same basis. And then it also has to sort the eigenvalues in the same order in order to maximize the expectation value. If you're very familiar with passivity, this I think is very clear to you. And if not, let me just say that it immediately gives you the optimal protocol you need to do in order to maximize the change. It does not necessarily optimize the Fisher information or the SNR, the signal to noise ratio, but it does maximize the change. And it has this added value that, as can be done usually in passivity, if there are some constraints on the allowed unitaries, that there are just specific interactions that we can use, it's possible to apply passivity to constrained interaction and get the optimal transformation under this constraint. So this is an added value of this approach that can be immediately applied to metrology. And finally, I want to say that typically this rho system as a function of lambda is a mixed state. And in my view, this motivates the study of mixed state, and in particular, non-thermal mixed states, because the derivative of the state, even if it's thermal for some lambda, the derivative will not be thermal, will not even have zero trace, unity trace. So it motivates the study of such states, even in isolated setups. Okay, going back to our main topic. So in periodic systems, Mark, I think I hear some background noise. Okay, thanks. So in periodic systems, there's a periodically driven system. We have this one cycle evolution operator U, and if we want to know the density matrix after k plus 1 steps, we just need to apply it to the previous density matrix. And now let's define this quantity that we call a stencil. It's simply a combination of density matrices at different times, where these AL coefficients are some real numbers, don't have to be positive. Now, it's easy to see how this object evolves in time, because since it is composed of density matrices, then to evolve it in time is just to evolve the density matrices. So it's just simply this expression if we look at R1. And more generally, we can write the expression for R after n cycles. Now, since this, by construction, this quantity evolves unitarily, we can apply global passivity to this object, and we'll also make this choice that f of x is simply x, and this will help us a lot later in order to connect the result that we get to actual observables. Right, so this is what we get. This is from the previous slide. And let's also make the choice that we look after one cycle. Okay, we don't have to, but let's make this choice and see what happens. And also we choose the simplest stencil, like the most basic generalization compared to just take row 0. So we take row 1 minus row 0. And now we expand it, and the details of the calculation are not important. I just want to show that we get two types of terms. One of them is like the blue ones, where it contains row 0, which we know. We know in which state we start the experiment, so we assume that this is given. And row 1, which we don't know, that depends on the unitary, but okay, we'll see soon enough what to do with it. And we have terms that we have two density matrices that we don't know, and that looks a bit more problematic. So if we look on the first term, we can actually identify it with an observable. This is the observable, and this means that we evaluate it after endpoints. We can write it like this. And this observable, and now I'm thinking about pure states, is actually the survival probability. What's written here is the chances that after n steps, I'll be in the same state that I started in. Now, in order to handle with these terms, we apply property of unitary periodic driving. And this is due to this choice that we made earlier, f of x equal x. We exploit it here. And we get that if we have a term like this, what matters is only the offset. There's actually kind of a shift in variance. So this expression is actually equal to R of n. Or in this case, it will be just R1, the survival probability after one cycle. So now we use this property, and we also use this symbol for the survival probability, and we get our first multi-point inequality, which you see here. And I would like to take this opportunity and throw at you this open challenge to derive this result from a different framework. And let me just say that I'm not trying to glorify the method I happen to use. I'm just really curious, and I think it would be very eye-opening to see how and if it can be obtained from other framework that were so far tuned to 2 points, but maybe they can be applied for multiple time points. And another clarification that I must make, these RKs are measured in different experiments. So if, for example, I have R1 and R2, it's not that I make measurements after one cycle and then I continue to propagate it and measure R2. To measure R2, I propagate the initial state for 2 cycles uninterrupted and then measure. And if I want to measure R1, propagate for 1 cycle and then measure, and the experiment stops. Okay, so there's no issue of collapse or the measurement affecting the experiment itself. So these inequalities have various aspects, and because there are more than 2 points, then there are different ways of looking at them, and one can see this already with 3 points. So we can take this inequality and rewrite it like this, and then we see that this is actually a lower bound on the value of R2 using this 2 points R0 and the previous survival probabilities. Now, I just want to draw your attention, and I'll show it in a second, that if we'll just use the regular 2 points, it provides an upper bound. It says that R2 has to be smaller than something. And here we are saying that it has to be larger than something. Okay, so it's already a difference. And one can also rewrite it like this. And this suggests that the total change in the survival probability, or the accumulated change, the survival probability, is smaller than what happens in, well, with a factor of quarter, than what happens in the first half of in the first cycle. And another way of rearranging it or to interpret this is the following, is to actually get information about the midpoints using the final points. So this is something like a conditioned prediction. We know what happens in the end, and from this given that we know what happened in the end, we want to say something about what happened in the middle. And again, just as a reference, if we look on the 2-point second law, and I apologize that this 2 point sounds a bit like the 2-point measurement that is used in fluctuation theorem, but it's actually completely unrelated. So when I say points, I mean points in time where we measure these Can you hear me now?
Yeah, just
Can
telling
you hear
Raam
me,
his sound just went. Uh,
Mark?
no, still not there.
Now? No, you can't hear me? Okay, so
Okay. I think it is actually. Sorry, hold on a second. I think it's actually somehow that can't hear it now.
let's try now.
Yeah. Okay.
Maybe somebody can write in the chat if
Yeah.
you can hear me.
This fixed it. Okay. Thanks.
Okay,
Sorry about that.
okay, good. So yeah, I was just saying that it's completely unrelated to this 2-point measurement that is used in the fluctuation theorem. So when I say 2-point second law, I just refer to this, which is to take the recipe of the second law and just apply it to survival probabilities. And then it gives this trivial predictions. Well, if you think about pure state, then R0 is just 1. And this tells us that the survival probability after one cycle is smaller or equal to 1, okay, which is very nice. And it tells also the same about the second point. Now, if we compare, for example, this is what we have here, then we also can express it in terms of prediction on R0 minus R1, but now we say that it's actually larger than a positive quantity, which is this. So this shows that this bound is clearly tighter than just what we get from the second law, which in this case happens to be also trivial and not useful. Okay, so we're done with the 3 steps. And now you can just choose any stencil you want. And here we made the choice that it's basically like the discrete derivative, okay, first derivative, second derivative, third derivative, and so on. But truly, you can make any choice you want. So for this, we'll call them later the SN inequalities. But you can take any choice and you'll get some inequality that will have this form, where WK refer to these funny coefficients, okay, and it's hard to guess where they come from, but they are a Fourier series of a certain function that I'll talk about in the end. And well, just kind of a curiosity. I mean, the signs of WK alternates; they must alternate, and that means that we can take all the odd terms that come in odd in time. That comes with a negative sign, and we can move them to the other side, and then we get a certain relation between what happens with the even points with respect to what happens in with the odd points. Another possibility is to transform this relation to the frequency domain using discrete Fourier transform and get a certain constraints on the amplitudes of different harmonics. Whether it's useful or not, I still don't know, but it's something that can be done. But as always, when we are facing too many possibilities, we're a bit baffled and don't know exactly what to do, how to apply it, and whether all of this is actually needed, or perhaps there is some more compact set that is tighter and better. And in this case, the answer is yes, there is a more compact set. And we can see this in this already in this 3-point stencil. And now we keep it as general as possible, where we put here coefficients A and B. So we plug it in and we get an inequality that we rearrange it like this. So we separated R3, we keep it here. And now we have some function that includes A, B, A squared, AB, and so on, and R0, R1, and R2. Now, in order to get the tightest prediction on R3 or the tightest inequality, we want this to be as small as possible. Now, the key point is that, and this happens for all orders, not just for the 3-point stencil, is that once the results of the measurements are given. So these become numbers. So this k is just a function of ab, a squared. So essentially it's a parabola. And we know how to find the minimum of the parabola. I mean, even I managed it. And so we find the minimum and the optimal a and b, the coordinates of this minimum, and then we plug it in, and we get this, well, less trivial inequality that you see here. It's nonlinear, as you can see, but it's not nonlinear like the entropy, for example. It's still composed of observables that are wrapped in some nonlinear function, okay? But so it's still simple to evaluate. And it's guaranteed that this bound is better than the S4 bound I've shown earlier, because S4 is a special case of this stencil. And what we did next is to apply it to heat leak detection. And we were curious to see if it actually helps compared to what we can do with global passivity. And I show you that the bound is tighter and in a specific case, but we are restricted to use these observables presently, which are the survival probabilities. While with regular global passivity in 2 points, we can use many other different observables. So it was not clear to us that adding more points will actually help because of this restriction to survival probabilities. And what we found is that we can detect heat leaks with pure states. So that, like, the input state of the system is just a pure state, and still we can detect a heat leak. This is something impossible with any 2-point inequality that is something that involves observables. Again, I'm not talking about entropies and nonlinear quantities. So this is already, the fact that we found even just one example shows that it can do more than regular 2-point global passivity. And another thing we found is that, again, I mentioned this earlier, that there is this limitation on the detectability of very hot environments. So there is a certain threshold, and above this threshold temperature, it's impossible to detect it using just observables with 2 time points. But we found that with 3 time points, we can detect beyond this bound. So these 2 examples are unique in the sense that they kind of breach the borders of what could be done earlier in terms of heat leak detection with observables. And next, we also applied it. Actually, we did this thing first and then this, but it doesn't matter. We applied it to, we tried to detect violation of periodicity. So these inequalities are based on the fact that we are doing in each cycle the same unitary. If we break this assumption, then potentially these bounds could be violated, even though the evolution is unitary. And we did this experimentally, and I will not show the results of this experiment. I chose to show the experiments related to this. But we saw that this is something that that can be done. Again, we're exploring the limits, and the same question that exists before for heat leaks, like, can we detect any variation, is valid here. Can we detect any variation of periodicity? And one of the motivation to deal with variation of periodicity, well, in the spatial domain, maybe it's interested to detect defects in a lattice. But in the time domain, let's say you repeat your circuit one time after the other, okay, just sequentially, And if your system is unstable, okay, maybe because your laser frequency drifts or something with the magnetic fields changes in time, then in principle that can be detected using these inequalities. I'm not saying that this is the only way, but at least this is something we can do based on this approach. And again, we don't need to know the details of the circuit. I think this is a major point, because if we do know what the circuit is supposed to do, of course we can check and see if we get the right result, and that's the end of story. But here we're thinking about machines that we don't know, we cannot compute what they do. Okay, so we can't just look at the results and say that it's right or wrong. So as for experiments, I want to show the one that involves heat leak detection with a pure state, and here we had a nice unexpected surprise. So we just wanted to show that it's possible to use a pure state to detect a heat leak, and the setup is very similar to what I showed you earlier, just smaller because it's a proof of principle. This qubit is the environment, and we're coupled to it. This part of the circuit is the preparation circuit. It creates the pure state, I mean, if we don't want to be in the ground state. And this part is the measurement. And what you see here is kind of a back rotation, because we want to measure in the same basis we started. Okay, and in the IBM, you cannot do this. You always measure in the same basis. So you have to do this back rotation. But these are details, and this is the circuit that we actually use, and this is the preparation of the pure state. So we started with preparing the standard computational basis in different runs of the experiment. And for this input, with the environment on connected, we got this value, where according to theory, we should get 0. But notice the uncertainty here is really small. Okay, so it's much smaller than this. And we did the same for 0, 1, 1, 0, 1, 1. So we didn't get any detection for this specific circuit. But when we use the quantum state, so we have a superposition now in the first qubit, then we got the detection. And just as a, again, reassurance test, we disconnected the environment with the same input state, and we saw that we don't have a detection. I remind you that negative value indicates a violation. Okay, so this is just to recap. Now, whether this is truly a notion of quantumness or quantum advantage, or I don't know. For now, I refrain to give it names. But I think it's interesting because the circuit itself is classical. If it's given classical inputs, it will provide classical outputs. Okay, it's not that there's something quantum inside. Only when you trigger the quantumness by putting a quantum input, then you can observe that actually it's connected to some environment. So to me, at least from an operational point of view, it motivates the use of a quantum state in the input. Right. So the fact that we can detect heat leaks with pure states, and also this detection with specifically with a quantum state, these are things that we were looking for. Okay, so it didn't came as a surprise, but the following was a surprise. We first observed this numerically when we looked on the actual value of this SN inequalities. We saw that actually the remainder, okay, or the actual value of this, of course, it's positive, okay, this is guaranteed, but it actually becomes closer and closer to 0. And then we found analytically that it's bounded by an exponential factor, exponential in the number of points. And soon enough, it doesn't take too much points. In our experiment, something between 5 to 15. For any initial state, it doesn't matter what is the initial state, we get that this inequality turns into equality. And okay, there's still an exponentially small factor here, but if this exponentially small factor is smaller than the experimental uncertainty from the noise of the experiment, then for all practical purposes, this is equality. So at least for us, this equality, again, applicable to non-equilibrium dynamics, was a surprise. Also, I worked a bit with Floquet systems, and I don't remember I ever stumbled on something like this. If somebody, it rings a bell to someone, I would be happy to hear and learn. To understand why this convergence takes place, convergence to equality, we need to take a short trip to Liouville space and introduce the principle of positivity. Before that, let me just show that from this equality, we can learn about the quality of the device. So first, I plot the values of RK for a specific experiment we ran. Again, it was a 2-qubit experiment. We did also 5-qubit. It's really not important for the present discussion. And I just put it here to show that it's not always the same, and also the change is not negligible. It's not that we took a circuit where the survival probability is always 1, and therefore, surprise, surprise, we got that this is actually 0. So if there is convergence to 0, we can extract R0 from this equality. And that means we have a prediction for what R0 should be in terms of all the other survival probabilities, starting from 1 and on. But we know what is the survival probability we start with. Again, in particular, if it's a pure state, the survival probability at time 0 is 1. So we know what we should get. And if we are indeed converged, this number should be 1. And here's an example for this circuit that we ran and for this circuit. And they were done also in different processors. So in this example, we got, this is after 10 cycles, we got very nice convergence, very close to 1. And here, it's also rather good, but not as good as this one. And potentially, okay, and I'm saying this with some caution, this can be used to quantify quantum processors, or at least to do relative comparison between processors. And this could be some figure of merits that can come out from this equality. Okay, this is maybe something that I found baffling, and I'll just quickly go through it. So I was curious, how come these coefficients W for a given number of points, they're fixed, okay? So how come we get convergence for different values of RK, for different series? If it was just inequality, then fine. You plug different series of RK, you get different inequality, different number, but it still satisfies the equality. But with inequality, I initially didn't understand, but this is actually because the sign alternates. And since the sign alternates, there are many values or many ways that you can reach 0 at the end. Okay, just kind of think of different trajectory that allows you to get 0. So, of course, if all the coefficients were positive, the only solution would be that RK is 0 all the way. Good. So now we go to Liouville space in order to understand this convergence. And let me give you, for those of you not familiar, let me give a crash course on Liouville space. The idea is to take the density matrix and to vec it, which means to turn the rectangular matrix into a vector matrix, to a vector. whose dimension is n squared times 1. And once you do that, the expression for the expectation value turns into a regular inner product between vectors, where this is the vect version of the observable A. If we look on the equation of motion, the Liouville von Neumann equation turns into a Schrödinger equation. And if the evolution is unitary, then this Hamiltonian will be Hermitian. So unitary evolution in Hilbert space is also unitary evolution in Liouville space. One cannot choose any arbitrary Hamiltonian like in Liouville space. There are some constraints on this choice, but we just need to know that it's Hermitian. That's all we need to know about it. And if we have n-cycle evolution operator, then we can write the density vector after n cycle. We can write it like this, where this is the evolution operator in Liouville space. Since it's a vector, then we operate only from one side, and this is extremely convenient when doing all sorts of derivation. Now, if we look on the survival probability, then this is the expression for the survival probability. But since this number is real, we can use the property of inner products, and we can write it also like this. It's the same thing, but it has slightly different interpretation because we can write this using UL, and since this is the bra, okay, this is maybe a bit too too detailed, but the point is that we get here U dagger instead of U. And the point is that because we work with survival probabilities, it doesn't matter if we put here U or U dagger. Okay, and this is something we'll use in a second. It's not true in general, but for survival probability, it doesn't matter if you propagate forward one cycle or, so to speak, backwards one cycle by applying the reverse protocol. So now let's look at the 3-point inequality and write it in Liouville space. So it has this form. And for any choice of row 0, for any density vector, we get that the result is positive. So this has the aroma of positive operators, right? What defines positive operators is that the expectation value is always positive for any vector. So it behaves as a positive operator, but this operator is not even Hermitian. So what's going on? Let's start with a simpler case, which is just the 2-point inequality. And now I'll use this property of that you can replace U with U dagger that I showed you earlier. And instead of writing U, we write this more symmetric combination. Now we can write UL, this can always be done. We can write it as the exponent of some effective Hamiltonian in Liouville space. And again, this Hamiltonian will be Hermitian. That's all we need to know about it. Multiplied by the evolution time. Now we plug it into this expression, and we see that it's actually 1 minus cosine this effective Hamiltonian. Now, since 1 minus cosine is a positive function, it immediately implies that G, defined as 1 minus cosine this effective Hamiltonian, is a positive operator. The operator was somehow, it's gone, but it's a positive operator. And if it's a positive operator, then now it implies that for any vector we put here, any density matrix will get a positive number. So we worked hard to essentially explain something that we already know, but now we can harvest the fruit, because if we know one positive function, it's very easy to generate new positive function, for example, by taking powers of it. And this time we'll take integer powers, not fractional ones. So this implies that this operator will also be a positive operator. It doesn't matter what is the choice of this h. In particular, if we make this choice to the power of n minus 1, one can show that this lead to the Sn inequalities that I showed you earlier. So we derived the same results, but there we used global passivity, and here we just use positivity. We just take one positive function and use it to construct positive operators and continue from there. So with this, we can state the positivity principle that any positive cosine polynomial function leads to an inequality of the form that I showed earlier, which is some weighted sum of the survival probabilities, again with alternating signs. So it can be something like this, or any positive cosine polynomial. Okay, and with this we can understand the convergence. So here I plot 1 minus cosine x to the power of n for different powers. And you can see that it starts to behave like exponential located at pi and minus pi. And in fact, there is a certain theorem that tells you that it converges to a Gaussian. But we use something slightly simpler. We just took a Gaussian function at pi and minus pi that bound 1 minus cosine, and then of course it bounds also the powers of this. Anyway, the details are not important. What is important is that this expression is smaller than 1 minus cosine x max, where x max is the largest eigenvalue of this function. So essentially what's written here is that this expression has some eigenvalues. If you take the largest eigenvalues, you get something which is larger than the expectation value. Okay, the expectation value cannot be larger than the largest eigenvalue. So this is what's stated here. And here we use the fact that you can bound the cosine, 1 minus cosine to the power of n, by this Gaussian. And we see here that it's linear in the number of, the exponent is linear in the number of points, which suggests that this actually exponentially goes to 0. And here's some experimental data for the value of Sn with one of the processors. And you can see that there is a bit of noise, and also, I mean, this result is, it was not done for very large values of n, but still it looks quite close to a flat line with exponential decay. And in fact, we don't care if it's exponential with some deviation. We just want it to go to 0 really, really fast. Fast enough that it goes below the noise level in the experiment. So from this, we can get a criterion for how big n has to be in order so that the inequality will behave as equality. And of course, that depends on the level of noise that we have in the system, the experimental noise. But let's say we want that the remainder of the sum, but the fact that prevent the equality from being exact equality, we want it to be, let's say, 100 times smaller than let's say R0 from 1, then it turns out that if x max is pi over 2, we just need 6 cycles. The reason I took pi over 2, because pi over 2 corresponds to a complete permutation. So if it's just a smaller rotation, it will be smaller than pi over 2. However, if the device is subjected to dephasing, dephasing can increase the value of this action and makes this x max larger than pi over 2, and it can be very close to pi. And this is why if you strongly dephase, you cannot see this convergence. You need to take many samples. But this is also something that you can learn. I mean, if you see that you don't converge, you can perhaps deduce something about the strength of the dephasing in this device. Let me proceed and summarize the main findings. So first we got this multi-points inequality for survival probabilities. We've shown that they're tighter than the 2-point inequalities. And also what's nice is that depending on the parity of the leading or the biggest, well, the final survival probability, that is after all the cycles, depending on the parity of it, if it's odd point or even, that determines if the bound on it will be upper bound or lower bound. So this is an interesting feature. We show that although there's a degree of freedom to choose many stencils, there are also, and maybe they could be actually adapted for specific applications where you want a specific form of inequality. But in terms of tightness, it's possible to optimize these inequalities and get for each n, you can find the optimal inequality. We applied it to heat detection and heat leak detection and saw that we can detect with pure states, and in particular, we can detect with quantum pure states where classical states, input states, could not detect the heat leak. And this was shown also experimentally. We saw, and this I haven't shown the experiment, and in fact, we haven't carried out this experiment to be more accurate. But this is something we should do soon. But theoretically or in simulation, we see that we can detect hot environments that are impossible to detect with just 2-point inequalities. We have applied it to periodicity variation, and here we do have experimental data, but I just haven't presented it for brevity. And we discussed this convergence to equality as the number of cycles increases, and we also shown experimental evidence to support this convergence. And now let me just show some fun ideas that you can do with this notion of positivity. So one can do what I call null engineering. So if you take a function that looks like this, it's a positive cosine polynomial, and the position of the null is known. Okay, this is the position of the null. So now you can take multiplication of several of these functions with different parameter b, and perhaps also take this one, which has a null at 0. This is what we started with, but we can essentially make any choice. And if we choose them smartly, we can, for example, put a null on this x max value if we happen to know it, or perhaps through optimization procedure, we can deduce it from the measurements, as was done in the other optimization procedure. Anyway, there's a way to construct bounds which will converge faster. Of course, there's a price for each null you pay. You need a new data point, but that could be a small price to pay. Another thing that we haven't explored, but I think it could be interesting because it may connect to what people know about transition probabilities and trajectories. Again, we can exploit the fact that this stencil could be very flexible. In fact, rho 0 and sigma 0 can be, or let's consider the possibility that they're actually completely different preparation but in the same experiment. So both of them evolve according to the same unitary, but this is a different initial state from this one. So now we haven't, previously we took different time points, okay? Here we take different preparations. And when we plug this in, we get something like this. Okay, this gn represents this function, or it could be something like this. It's not really important, but we see that one can split it and write it as two terms that relate to survival probabilities, or deal with the survival probabilities. And here it's actually transition probabilities. It's the chance that if I start in sigma 0 and let's say I propagate for n cycles, and I'll end up in row 0. So let's assume that these two subspace, row 0 and sigma 0, do not overlap. So it could be that they are just orthogonal functions, or they can be orthogonal subspaces. It doesn't matter, but the point is that it gives us this probability to end up in the other subspace. So this is something that we still haven't explored, but I think it could be interesting. To conclude, let me put this code here that generate these coefficients, these W coefficients. So you just change the number of cycles here, and it spits out the coefficients. You may play with it. You may apply it to systems you work on, or anyway, it's here for you to use. I apologize that you cannot cut and paste. If you're really interested in the piece of code, just send me an email. But it's for you to use. And finally, let me thank my collaborators, Sar Rahav from the Technion in the context of global passivity and passivity deformation, Nadav Katz from the Hebrew University that helps us in the context of the IBM experiment.
Hi, Raam. Sorry, can you hear me?
Mark.
Hi.
Yeah.
Sorry,
Yeah, so
my computer decided to freeze at exactly the wrong moment, so I was not able.
which moment is that? I
Well,
mean,
no,
how
no,
long have I been talking?
no. I think the timing was perfect in the sense that that you got through to exactly the end of the talk. The problem is that my mic was muted, so I couldn't tell you what happened. So, but
Okay,
we
good.
are. So I don't think any of your talk was lost. I think the point is we can go straight to the question and answers now. So and of course you also missed me clapping, but thank you very much for a very nice, very interesting talk. And I also want to say, I mean, I really appreciate the code snippet as well at the end. That's a really commendable kind of approach to open science. So I really like that. And yeah, so we already have a couple of questions. We have people, of course, kind of clapping and saying thank you. And I encourage people to ask further questions. You can just write them in the YouTube chat window. So let me just go through the questions in order. So the first question we had from Michael Moskelets, which was actually about some material at the beginning of the talk. So the question was about a possible connection with the Rainey entropy. I mean, a fractional power. So I think when you were discussing
Yeah,
at the beginning of the
so,
talk before you got to the periodicity stuff.
right. So the Rainey entropy and the free energy inequalities in resource theory, they are not observable quantities. And it's not clear how to relate them to observables. Both of us use the letter alpha, and that's a connection. And we also have a continuous family of constraints. Of course, what's strong with the Rainey entropy and with resource theory is that if all of them are satisfied, then you can deduce that there's necessarily a transformation, that there's a certain realization that implements the transformation you're checking. And this is not something that can be done with these inequalities. They're not, in a sense, a complete set or something like this. But analytically, I'm not aware of any connection because it involves all sorts of fractional powers of the density metrics, not of the observable.
Mm-hmm. Okay, thank you. So then we had a question from Stefan Nimrichter. So I think the question was probably about when you were showing the first set of experimental results. So the question is, does that mean that you were detecting a dephasing channel? So I guess this is referring to the first set of experimental results.
Well, for the first experiments, no. When we did the heat leak
Sorry, no,
detection,
not the heat leak. I mean the regarding the periodicity. So when you were showing experimental results for the periodicity part of the talk.
oh, so yeah, the fact of the mechanism that prevent it from converging to one is, yes, it's dephasing. A heat leak can cause a violation, but dephasing slows down the convergence. But the problem is, to quantify this dephasing, you need to know what is the action of the bare circuit. Okay, so in order to get a number on how strong the dephasing is from this equality, something else has to be done. Okay, some information is needed. And we're not there yet. So it's an interesting question.
Okay. Hopefully that answers the question, Stefan. If it doesn't, then of course you can clarify. So we had a question from Susana Huelga, who says, "Thanks for the talk. One basic question: how can I easily understand that the concept of global passivity leads to bounds on system environment correlation? Should I read your PRX from 2018?" I guess he's going to say yes, you should read the PRX, but
yeah. No, I mean, okay, the observables, like for example, the second power of this operator, the sum of beta h, okay? So the first power, just get the standard second law. But if you look on the second power, you already have mixed terms like h cold times h hot, okay? And that already probes the correlation. Now, it's not written nicely like a covariance. Okay, this is one of the problems with inequalities. You can add them, okay, but you cannot subtract. So you cannot always wrap it, these global passivity inequalities, in a form which is convenient and extract the information that you want. With passivity deformation, there's much more flexibility, and it's possible to turn it into something that you want with quite a bit of limitations, but this is something that can be done. But I wouldn't say that this is like offers a generic answer to what is the correlation build up between elements. Maybe in a specific case, but not generically.
Okay, thank you. Okay, the next is from Yaron Ilan, who asks, do you see any applicability to biological systems?
So first, regarding, I would say, stochastic systems, then I think it applies because since this is not sensitive to dephasing, then you can always assume that you have a unitary, and then right after it in the cycle, you have a very strong dephasing stage that erases all phases. And that means that the evolution operator is just doubly stochastic metrics, okay, which it doesn't represent all classical possibilities, but it could potentially be applicable to more classical systems, in particular about biology. I mean, I know nothing about, but I'd be happy to discuss in private and maybe learn something. Yeah.
Okay, thanks. I mean, I guess the question also made me think about these kind of multi-point measurements that are very common in quantum biology. I mean, this kind of two-dimensional spectroscopy and so on, this sort of pump probe
Mm.
kind of measurements. Um, but I don't know if there's any connection there, but I mean, they are kind of able to measure these higher order kind of multi-point measurements. So I wonder
Right.
if that would be
Okay.
the
So I
connection.
guess I'm really not familiar with this, but okay, now I understand the question
Well,
better.
well, this may not have
And
been the actual question, right? But okay, anyway,
okay, but
let's
it's
talk
an
about it anyway.
interesting connection, and it's interesting to look into it. But I'm really can't say anything from the top of my head.
Sure. Okay.
Interesting though.
Okay, all right. Thanks. So let's move on to another question from Stefan Imrich again, who says, okay, so in metrology there are the multi-pass schemes in phase estimation where you get a better signal-to-noise ratio if you send a qubit in multiple times. Do you think
Hmm.
that you could use your SN inequalities to outperform such a multi-pass measurement scheme?
Sorry to
To
outperform.
outperform such a multi-pass measurement scheme?
Um, so I don't think okay. I don't think they offer necessarily a protocol. The inequalities. They just give you bounds or sometimes equality. Uh, on the other hand, and maybe it was confusing to put these two things together, but the idea of passivity itself that also leads to inequalities, global passivity, but on the other hand, it also leads to the optimal protocols in many cases. So this is what I was saying in the context of metrology, and I haven't thought about applying. Okay, maybe I should have applying the fact that passivity leads to optimal protocol, but optimal protocol in multi-time points. So this is something to think about. So thank you for and Stefan. We can discuss it later, but it's interesting.
Okay, thanks very much. Um, so okay, I mean that's it for the questions so far. Maybe I can just ask a quick question. If anyone else has any further questions, then feel free. But I mean, maybe I just missed something. But I mean, how complicated does this become? These inequalities become once you really start considering lots and lots of time points. I mean, because you were mentioning mainly the advantage of 3 points versus two, but what's stopping me going to 10 points? I mean, is it just very difficult?
There's nothing. I do experiments with 10 points, and
Hmm.
essentially the limitation is how many jobs IBM lets me send sequentially
I
because
see. Okay.
I don't want to do it in different days because this is calibrated each day, and then the system is not stable in this time scale. So it's not meaningful to separate in times too much, but essentially it doesn't cost anything. And in fact, what we want to do is to go really to something like tens of cycles, maybe 100, and actually try and see a violation due to the intrinsic losses of the machine itself.
Hmm.
And this is something, I mean, if it's just a few cycles, it's way shorter than the T1 and T2. But for dozens of cycles, we may be able to probe the actual heat leak of the machine, and I think this would be a nice demonstration. But it doesn't to generate these quantities. Again, it's a Fourier series of some function. I mean, I don't think that even 1,000 cycles is a challenge for a PC. Okay, or
Mm.
um,
Okay. Cool. Thanks very much. All right. So I think that's hopefully I got all the questions. If there are any further questions, I'm sure Ram will be open to you just emailing him and discussing that way. But so let's conclude it there. So thanks everyone for tuning in and for putting up with the technical issues as always. I apologize for that again, and I'm sorry to you as well, Ram, for this. But I don't think it got in the way. You were able to get everything through there eventually once I
yeah.
sorted it out. But most importantly, I want to say thank you very much, Dr. Raam Uzdin, for a really nice talk. Cheers, Ram.
Thank you all. Thank you.